Thank you so much, Dr. Martinez, for doing this. I'm Seth Bornstein. I'm a science writer here at the AP. Congratulations. So apparently your wife said you decided to sleep first, right?
Well, my wife is very kind and she knows I need my sleep. So she waited till 5:30 or so to let me know. So that was great.
Are you glad you slept, or would you have rather been woken early with
No,
this?
no, she did the right thing. My wife has very good instincts on what to
Wonderful.
do.
Hey,
So
So,
Mark, really quick, could you turn the phone horizontal?
Sure thing.
Thank
so
you.
what, so what, so what,
you gotta make
did you
fun of
hear?
that.
How did you hear? Was it from your wife?
Yeah, she woke me up and mentioned that there's some reporters who wanted to talk to me. And, I kind of put it together and I just looked on the internet and, saw the slide and my picture with Michel Devoret and John Clarke. So that was kind of an interesting way to find out.
It is. So what does the prize mean for you?
Excuse me?
What
What
does the
does the
prize
prize
mean for you?
mean for you?
It's I don't know. It's just a really big honor. I was just thinking this morning that it was really wonderful to work with John Clarke and Michel Devoret in graduate students to do the first experiment on this, and they're just such great scientists. And it was a great experiment to work on. A fundamental question. Turns out a lot of practical things came out of this, a lot of people doing research, but I really like working with them because it kind of trained me how to be a scientist on a very important question and how to do science correctly. And um, I'm just, I think the prize means that, we tried to do the experiment really well, be a good scientist, and I just feel very honored to kind of be awarded the prize for that whole body of work. And I would say, after that experiment, a lot of people got involved in this, and I would say people did the research and investigated this physics in a really good and scientific way and understood what was going on. And I'm just really happy that we were able to kind of seed the field in a way where people did very good science. And I think that's why we've been successful over the years, going from that basic experiment all the way now to people are trying to build a quantum computer. That success has been because I think we really tried to do good science in the very beginning and really understand what was going on.
You talked about fundamental applications. You're dealing in the weird weird quantum world. How would you say your work has changed our everyday macro world?
So people to describe quantum mechanics of the physics of very small things like atoms or electrons, things like that. And that's the way people kind of thought of quantum mechanics at the time. But during that time, Professor Tony Leggett, who's won the Nobel Prize for something else, postulated that maybe when you get to the size of big things, macroscopic things, that quantum mechanics would not be obeyed. And in the particular case, you're seeing quantum mechanics in a circuit made of many billions and billions of atoms, and you're looking at quantum mechanics of the currents and voltages that are flowing in the circuit. And it was to test what we were doing was to see if quantum mechanics would work in these kind of macro big systems. And it does. And that's what we proved very, very clearly with some fundamental quantum mechanics behavior. And in the end, it kind of opened up people to say, well, we can design our own quantum mechanics systems. Our playground is not just electrons and protons and atoms or whatever, but you can actually build electronic devices or other devices where you could observe quantum mechanics. And, it started with electrical circuits, and there's other things people are looking at now. Now, in terms of applications, what happened is around this time, people started thinking about using quantum mechanics to do quantum computation. And, since we build computers out of electrical circuits, it's very natural to look that way. So it's been, many decades of research, people trying to do that with myself and Michel Devoret and John Clarke, many other people. And it's nice to see that, eventually there's a really good likelihood that we're going to be able to build a quantum computer out of these systems.
One of the things that's been said is that that our cell phones today have an application of your work, or is that a little much of a stretch to say that? Would you say the cell phone that we're recording you on was improved or made possible in some ways because of your work?
I don't know about the cell phone. Certainly quantum mechanics tells you how transistors work and the materials in your cell phone work. This is kind of going beyond that and looking for a computer that's using quantum mechanics application. But, certainly we use a lot of technology that's in the cell phone, especially the microwave transmitter and receiver part of it. We use that, and that's going to help us to make our quantum computer more cheaply, which is a good thing. But I'm really interested in using the quantum computer, when I build a quantum computer, to be able to solve chemistry problems and materials problems and simulating transistors better. Because in the end, reality of nature is that it obeys quantum mechanics. And that's where you get all these interesting behavior from materials. And if you build a quantum computer, you should be able to simulate that better in a variety of ways to build even better materials and solve lots of technology problems.
And for the average person, you were just about saying this, but the reason quantum, they're so used to, they think the computers we have are powerful and fast now. What's the difference between what we have now and quantum computing that you're leading to?
Well, one of the great things about my career is I started from these basic experiments, and then in 2011 I was able to move to Google, and we published in it was after 2011, 2014. We were able to do this quantum supremacy experiment. And what that showed is, for a very simple mathematical algorithm, we were able to show the quantum computer was powerful, where we can take data with a quantum computer. In order to simulate and understand that data, it would take a big supercomputer thousands of times longer than that. And that has been also demonstrated by other people. Google, since I left, has also been able to show that even on bigger systems. So to me, that was a really great experiment, that you show that the quantum computer could be much, much more powerful. What we have to do is go from that mathematical problem to a more useful problem. And that's what the whole field is trying to do now. There's a lot of interest to show utility for the quantum computer. That's the area of research right now.
And for the everyday person, it's very hard to get their heads around the quantum world. The idea something can be on and off, or penetrating an impenetrable barrier. How do you describe to people who aren't physicists the quantum world and quantum tunneling?
Well, what's interesting is, if people are aware of how regular computers work, you have a transistor that's on or off. That represents a 0 and 1, encodes a 0 and 1. And then you put a bunch of those things together to do a computation. What the quantum computer does is allows you to have both on and off at the same time, which is a very difficult concept to understand classically, but that's what happens with quantum mechanics. And what it means is that you can do a computation both on and off at the same time. And it's kind of like a parallel processor. Okay, so for one bit or one quantum bit, that's a factor of 2 in processing the 0 and 1. Okay, that's nice, but not fundamentally useful. But what happens is if you make many qubits together, like 2 qubits, that's in 4 possible on-off states. 3 qubits is 8, 4 qubits is 16, and the size of parallel processing grows at an exponential rate, to the power n. So, by the time you would get to, a few hundred qubits, 2 to 200 is bigger than the number of atoms in the universe, okay? So you can really do some powerful computation. Now, to actually take advantage of that takes some work. That's why we've been working on decades to do that. But I really believe it's possible, given enough time and effort, which people are putting in, to make those kind of computers a reality. So it's just quantum mechanics allows you to process information in a fundamentally new way that kind of gives you this parallel processing, as I just discussed. I hope that
Oh, yeah,
works.
that helps very much. Thank you. So, any other thoughts about what your research means to the world as well as to you? I mean, to your neighbors and your wife, assuming that she's not a physicist. She might be, so I apologize.
I think, people understand these days how important computers are for our life. I mean, look, we're talking about a cell phone thousands of miles away. And, it's just in everyone's life. And we're optimistic that we can use the full laws of nature, the full quantum mechanics laws of nature to actually do computing. And then we can solve, problems that are really quite intractable right now. And that will help humanity. I mean, the big thing that I'm interested in is doing chemical simulations, material simulations, to make better materials, maybe make better energy processes or the like, which can really solve a wide variety of problems. Just like computers, initially they had a small niche application and now they're everywhere. We're thinking that, with quantum computation, a similar kind of, ubiquitous applications and benefit to humanity can happen from this. And that's why, a lot of people are working on it. It's very exciting to think about, building a much more powerful computer.
When you got into this field 40, almost 50 years ago, were you thinking more about the actual quantum physics and the fascinating world there, or were you more thinking about sort of applications in computers? What drew you to this field?
Well, I just liked Professor Leggett proposing that this was an important experiment to do to see if quantum mechanics can work on this macroscopic scale, work with, currents and voltages and enter in a new class. So it was purely a scientific kind of endeavor to do that. However, at the end of my PhD, I came down to Santa Barbara and they have a conference on this very topic. And the last talk of the conference was Richard Feynman, who's a personal hero of mine.
Yeah.
Very famous in physics, gave a talk on quantum computing. And that was the first time I heard where you can maybe use this physics for, doing more powerful computation. Now, the interesting part was, after he gave the talk, we went out to lunch. He was totally mobbed by all the physicists, asking him questions and what would be like. Now, I was only a lowly graduate student, so I was way far back and could barely hear him. But it was very clear that this whole topic would be very exciting for physicists and very popular and, something you would kind of want to spend your career doing. okay, understanding how to turn this very basic science into a quantum computer. And that'll happen at Santa Barbara. I very much appreciate that.
Wonderful. Any other things you wanted to say that we didn't ask you?
No, I'm just really pleased, and I'm excited to talk to Michel Devoret and John Clarke at some point today or next few days. And really, like I said, I really wanted to thank them for what that meant for my career, irrespective of the Nobel Prize, to be kind of trained by them and then mentoring me on how to become a good scientist was probably the greatest part of this whole adventure.
Was there a point anywhere that you just thought this is too difficult? I'm going to give up?
Can you ask that
I'm sorry.
again?
Was there any point where everything became so difficult or so intractable you wanted to give up? And then what happened to keep you going?
Well, actually, in my PhD thesis, I had problems fabricating some of the devices, and that was kind of hard for me. Little did I know that that was normal when you actually make things. That was probably the closest. I'm never close to giving up, but I certainly, had a challenge. But that's part of doing science. I think that was a good learning experience. But I just enjoyed working on this problem my whole career. And I would say I did work at Google and left Google, and it was really kind of great for me to think about how is it that I wanted to build a quantum computer and form a startup company to kind of build that in the way that I thought needed to be done. So that was, it's been a hard couple of years to kind of restart my whole program to do research, but that's been really great because it's freed me up to be very creative and think kind of out of the box on how we're going to build this big system. And that's been just a wonderful experience.
I so much appreciate it. Mary, if you have any questions, jump in. But I want to thank you and congratulate you for this and talking with us. And
Thank you very much.
Hi there. Congratulations. I actually have a small request. Since we normally do these Zoom interviews on a computer setup, I'm wondering if you might have just a few more minutes to switch to your laptop or computer, and we can kind of just do another few minutes talking that way, just because this phone recording situation is not ideal for our TV audiences.
Okay, yeah, I can talk a few more minutes.
Okay, great. Do you want to?
I want you to do to switch to your laptop.
Yeah, if you want to provide him with this Zoom link, I'll just stay here, and then when you're ready, you can log on your computer, and you can just ask a few more questions in that format. That would be great.
And you log in
Sure, absolutely.
Perfect.
and,
Okay.
and you log in your computer.
I'm going to log off now.
Okay. I'll see you in a few minutes. Thank you. Hello again.
Hi there.
Thank you so much for doing a quick redo, essentially. I'm going to just ask you some of the same questions that Seth just talked to you about. So first, can you just say again, how did you hear about this announcement, and what was your first reaction?
Well, my wife woke me up a little bit before 6 in the morning, which she normally doesn't do, because she
Recording in progress.
my wife woke me up a little bit before 6 in the morning, and she had heard from you a couple hours earlier, but she wanted to make sure I got enough sleep today, which actually she understands me that's important. So she said AP wanted to interview me. And, I kind of knew that the Nobel Prize announcements was this week, so I kind of put two and two together. I opened my computer and looked under the Nobel Prize 2025 and, saw my picture along with Michel Devoret and John Clarke. So I was kind of in shock. And, so just been thinking about it and talking to the reporters here. And I just opened my email. I have a lot of incoming email that I'll have to answer. So it's kind of a shock. The Nobel Prize Committee kind of has conferences and they talk to people. So, I knew it was a possibility for quite a few years now. I'm just so busy this year, I kind of forgot about it until this morning. And, obviously that's just great honor. We're really, this year will be an adventure for sure.
Yeah, I mean, I'm sure you're still processing it. This is all so new. But really, what does this prize mean to you?
Um, I'm just, really honored that to be able to do an experiment where you even have the possibility for the Nobel Prize is kind of unusual because, we do a bunch of physics research over the years, and some of it's important and some is just good science and the like. And, I'm just honored that, I was able to do an experiment as a graduate student that in the end had this kind of notice. And in the beginning, it was very nice, but then because of the concept of quantum computing that's brought about by other people, this became more and more important. And now it's a huge field. Thousands of scientists are employed trying to build a quantum computer. I'm trying to do that too. And I just think it's great that all this came out of this basic research. And we have a really lots of interesting jobs for young scientists to try to build a quantum computer, understand the science and engineering. And I think that's great that everyone's working on this.
Yeah, and I mean, outside building the quantum computer, how can you explain this to the everyday person, to the layman? Like, how has this work that you've done changed our world?
Well, people are used to the idea that quantum mechanics is how, atoms and electrons and protons work, how very small things work. And, you have to take a physics class to really understand that deeply, but people generally understand that. But the thesis was by Professor Tony Leggett at this time was maybe quantum mechanics didn't work on the macro scale. Okay. And no one had ever really proven that before. So what we did is we built some electrical circuits where the current and voltages actually obey the laws of quantum mechanics in detail. And it really showed that quantum mechanics just wasn't some phenomenon on how atoms work, but it's actually very general and how really any system under the right conditions can see that. So that was kind of showing quantum mechanics had a wider application class than we had thought. But then, of course, what's happened over the years is people have thought about building a quantum computer. In fact, I first learned about that from Richard Feynman at a conference in Santa Barbara, interestingly enough. And a lot of people, myself included, many other people have been interested by that challenge and taken this and try to build a quantum computer, which promises to be much more powerful than the classical computer for certain problems, but important problems.
And so how would you say that this is really changing our future or our present?
Well, right now, people are trying to use these devices to build this powerful quantum computer. And I think we've shown that a powerful computer can be powerful. This is what I did when I was at Google with something called the quantum supremacy experiment. But that was for a mathematical problem. Okay, it's good for showing that the science is right, but people are working right now to solve real problems. And it's an active field. Lots of people are doing it. I've done the startup company to help try to build a quantum computer, working with lots of other people to do that. And that's something we think for the future. Okay, can we build a quantum system big enough, good enough, high enough quality that you can solve these problems? So the problem that I'm interested in is doing quantum chemistry. Okay, Supercomputers these days used to solve chemistry and materials and let's say how transistors work in detail. Use a big supercomputer because quantum mechanics is so difficult to simulate. Okay, and it's very clear, and this is Feynman's idea, that you can map these chemistry problems, these difficult problems, onto a quantum computer, and given the natural power of the quantum computer, you could then do that much faster. So there's other applications too, but that's one that I see is very practical and useful for the world because if we can build better materials and let's say, use the materials we have abundantly instead of, rare earth materials or things like that, use them more smartly, then, we can solve a lot of technology problems. And that to me is what's really fascinating. Try to do that.
Yeah,
Can
that's
I
really
just
cool to hear the real world
Oh,
application.
but by the way, doing that requires a huge team of scientists to figure out from the bottom end of the hardware going all the way up to how to do the software and the like. And our company is, working with a bunch of other companies and scientists to do that. And I just find it very exciting to work on a big team to solve a big challenging problem. This is not easy. And especially in the hardware end, my end, okay, we still have a lot of work to do. A lot of science, a lot of engineering. It's just a real pleasure trying to figure this out. I really believe we can build a quantum computer, given enough effort and time and resources to put it all together.
how far away do you think that quantum computer is? And if you don't mind, can you tell us how to pronounce the name of your company? I love it as a Scrabble player. I mean, I would wish
Yeah,
it would.
that's right. That's right. That's going to be good. It's called Colab. And it's a mixture of for quantum and collaboration. So what we're trying to do in our company is collaborate with a bunch of other, let's say, semiconductor companies, very well established, as well as startups and like, but working on a collaboration to build a quantum computer. So that's kind of the origin of it. But I'm glad it's going to help with Scrabble players. That makes me that make very
How many
happy.
how many years away would you say the quantum computer that you want is?
So this is always a question, and I always kind of put it off, saying research or whatever. But what happened is last fall we submitted a paper to archive. We'll get it published in a journal, talking about how we want to build a quantum computer. And there's this nice government program right now that's investigating and thinking about benchmarking the quantum computers. And the timeline that's given is 2033. So that's, let's say, 8 years, 10 years away, something like that. And I think we have the ideas and made enough advancements that is really possible, given enough resources for what we're trying to do. So this is the time scale that people are really pushing forward in terms of building something. I'm going to say it's hard. And then if you look at the progress over the last 5, 10 years, there's been progress towards that, but we have to make faster progress. And our paper that we published gave ideas on how to get there faster and do things faster. So for example, one of the things we're doing is we're working with a semiconductor tool manufacturer called Applied Materials, very well known in this space, who makes the tools for all the semiconductor processes. And we decided to work with them in order to make the qubits better. And also, if we can make them better, they're using the modern 300 millimeter tools, that you can use advanced fabrication to, scale up rapidly. So we've been thinking very hard about how to do this much faster.
And I have a colleague who wants to know, how does AI fit into all this?
So AI is kind of a different kind of algorithm. However, what our particular team has been thinking about is using a quantum computer to generate data so that AI can train on that data better and then make better predictions doing that. Because as you well know, AI needs a lot of data to do that. If you're trying to solve scientific problems, especially chemistry problems or materials problems, you have only so much data. And we're thinking that using a quantum computer to synthetically generate data can help the AI learn faster and solve these problems faster. There's other applications kind of for that. At Google, I work for the quantum AI group, so they were definitely thinking about that at Google. But this is what our company and our consortium is focusing on. And we think there's a lot of value in doing this.
I know we've taken up a lot of your time, and I'm sure you have a lot of messages to respond to. So thank you so much for doing this. If there's any other last final thoughts you want to share, please feel free. But otherwise, thank you so much.
It's just a real honor, and it's great that it was such a wonderful time as a graduate student to work with John Clarke and Michel Devoret, which really trained me how to become a scientist. And it's just a real honor to have the prize with them because that meant so much to my career. And it's great that I was able to do my PhD thesis kind of over and over again. This is what scientists like to do. They like to go back to their PhD thesis. So I've been able to do that my whole career, and that's been quite fun.
Oh, do you know where Michel is right now? We've been trying to track him down. Is he there
Yeah,
in Santa Barbara?
I know he lives in Santa Barbara, but no, I don't know, unfortunately. He's very busy, so he could certainly be traveling. But he might have just, not woken up this morning. You have to try
Um,
him again.
does he have the same position you had at Google, or is it a different one?
At Google, I think he came in more as a consultant. I was leading the hardware group. And then for the last year, other people led the group. And it's kind of part of the reason I left. But Michel is more of a consultant there. But he has a research group at UC Santa Barbara.
Yeah,
And stayed in touch with his academic side of him. So
perfect. Thank you so much. Congratulations again, and we really appreciate your time.
Yes.
thank you very much.
Thank
Appreciate it.
you. Nice
Nice
to meet
talking
Thank
you.
you.
to you.
Bye-bye.
Okay.
Bye bye.
Bye bye.
I hear it's time for breakfast.